Hey, good morning, Sam. How are you?
I'm doing well, Richard. How we doing today?
Doing great, doing great. We were just off air for a second talking about football, and maybe we could just do a whole podcast on that. That would be great.
It would be awesome. I'm a former football player from Princeton, so it's one of my first alums, right?
I love
So
it. Yeah, I think it would be fun, but not this time. Next time potentially. But Sam, welcome to Rare Awareness Radio. Just for the audience, I'm just going to let folks know we're here with Dr. Sam Young from the University of North Carolina. Got some branded logo wear on there, which is great.
right.
Sam is the director of the Gene Therapy Center, but he's also a professor of pediatrics and pharmacology at the University of North Carolina, Chapel Hill. So welcome, Sam, and we're really excited to talk to you today. We've got some great people in common, right, through the CACNA1A Foundation, and I know that's an area that you focus on, but there's a lot that you focus on in terms of your
Yes.
research, in terms of your scope. Um, let's start there, Sam. Let's just start with sort of that, areas of your focus. I would
Sure.
love that, and just some background on yourself as well, Sam. You mentioned
Yeah.
Princeton,
So
but you got a cool background too.
yeah, I can give you the nickel tour of,
Yeah,
of how I
awesome.
got here, and it's kind of I would almost say like the classic American story was. I grew up in Caldwell, New Jersey, and
Nice.
the old saying about New Jersey, only the strong survive, right? And neither my parents were college graduates or anything. And then my
Yep.
older brother was the first one to go to college and graduate, and then I followed, and I went to college, wound up playing football at Princeton University for 4 years. We're the 1995 Ivy League champions, right? Which was awesome. But
That's great.
my sophomore year, I decided I wanted to major in molecular biology at Princeton, and I was fortunate enough to have Arnie Levine at that time point, to let me work in his lab to do all these things, and I really did a lot of work in science there. And then I decided after I graduated Princeton, I wanted to do my PhD, which
Okay.
was uncommon for football players, right? And so
Right.
I went
Sure.
down to UNC Chapel Hill and wound up doing my PhD with Jude Samolsky. And that was from 96 to 2000. Did my PhD in 3.5 years. And
Wow.
for those that know Jude is super famous in the field of gene therapy. But
Right.
at that time in the mid to late 90s, gene therapy was just an idea and just
Right.
kind of
Yeah.
taking off. And we were living through the destruction of gene therapy at that time point for the disasters that had happened.
Mm.
Jude has since gone on to incredible fame and fortune with his companies since then. But after I finished with Jude, I decided I would wanted to move into the field of neuroscience because at that
Mm.
time things were moving where they were sequencing the human genome. We were
Right.
starting to get an understanding of genes, and my big idea at that time was I was going to take my ability to understand virology, as
Mhm.
Arnie Levine would say, if you're a virologist, you can do anything, right? That's the
Right.
best training in the world.
Yep.
And so I decided I was going to shift into neuroscience and completely shift fields. And I went and worked with Chuck Stevens, who's deceased now. Chuck gave me the opportunity to work at the Salk Institute,
Oh,
where
wow.
I worked on synaptic physiology. I had to
Mm.
understand, essentially, do patch clamp electrophysiology, complete shift of the field, something I'd never been trained in.
Mm.
And what I'm doing here is building up to how I got here. And so there I was working on how do I develop viral vectors to transduce neurons so we can start to do genetic perturbations. And
Mhm.
then I spent 4 years with Chuck and had gotten some headway. And then at a chance meeting at a Gordon conference in the summer of 2004, I met
Okay.
Erwin Nair, Nobel Prize winner, right?
Sure.
1991 Nobel Prize winner. And Earl and I were chatting, and I've been working on a lot of virology, developing methodology to transduce neurons. Neurons, as you know, Erwin is a world class biophysicist, synaptic transmission, right? And Erwin's just a wonderful human being, also. But Irwin at that time wanted to be able to do molecular biology to understand, how neurotransmitters really work and combine molecular biology
Mhm.
with biophysics and to get a quantitative understanding of synaptic transmission.
Mm.
And so Irwin and I agreed over at a Gordon conference on a one night over over a beer. And that's a story unto itself. But we had
Yeah.
decided I'd moved to Göttingen, Germany. I'd never been to Germany or Europe in my life.
Wow.
And then sight unseen, I decided to join a week later, as a personal story, I met my wife in San Diego a week after I agreed to go to Germany,
Germany, of
and
course.
didn't tell her that I was doing this for a few months. And
That's great.
anyway, after that, I mean, we're happily married now, almost
Right.
20 years, and we've got 2 kids and all this other stuff, but that's life for you. So I spent 5.5 years at the Max Planck Institute for Biophysical Chemistry with Irwin,
Mm,
and that's where I really started to develop adenoviral vectors, right, for the ability to transduce neurons to be able to study at the biophysics level. And
wow.
I'm going to go into that to tell you why that was
Yeah,
important,
why that's
right?
important to us. Yeah.
And so then after Irwin's, I went down, started at the new Max Planck Florida Institute for Neuroscience, where I really started to really develop more adenoviral vector technology, then to eventually combine this to solve problems in neuroscience at the auditory level, and then
Mhm.
started to shift focus onto inner ear gene therapy.
Okay.
And so the Max Plancks, for those that don't know, they have this you can't stay, right? It's an independent group leader position where they have this philosophy that you invest in people, not projects. And the best science you'll ever do is when you're at the bench, right? In that
Wow.
early stage of your career. But
Right.
then they want you to move on. And it was an amazing time there. So year 5, we've been doing really well, and I had to look for new positions, and then I wound up going to University of Iowa because I
Right.
was really interested in inner ear gene therapy. They have the top 5 otolaryngology department in the country, and not only that, they are heavy into otology, and Dr. Marlon Hansen and Bruce
Mm,
Vance were there, so we collaborated to work on inner ear gene therapy. But at that time point, we'd been establishing working on calcium channels. And so then I started saying, well, we're going to use this vector to go after large genes. And this will be the context to set you up of how we got to where we are.
sure.
And then about 2 years ago, I was, minding my own business. And then out of the blue, I got asked to be recruited for different positions. And then I got a call from UNC Chapel Hill. Would I be interested in coming back to run the actual gene therapy center that I did my PhD in?
What
So,
an unbelievable, like,
yeah,
full circle story. I mean,
yeah.
I was trying to do the math in my head, Sam. That's like, what, a 12 or 14-year span? Did you say?
Let's see, I graduated in '96 from Princeton, and
Yeah.
so it's been a lot. I've moved a
Yeah.
lot. What
Yeah.
was interesting was when I was here at Carolina as a grad student, Mac Brown was the head football coach, and they were great. And when I came back, Mac Brown was still the head football coach, and he had moved around too.
Because spending your career following Mac, that's funny.
That's right.
That's
That's right.
that's really great. I mean, the amount of Nobel laureates and people that you've had the opportunity to study under, it's fascinating, Sam. I mean, you have a fascinating story. You really do.
So it is
Yeah.
fascinating, and what I try to tell people is that you're driven by questions, right?
Yeah.
And
Yeah.
so for me, I've always been driven by questions that I want to answer, and you want to answer generational questions, right?
Mm,
And individuals that are doing elite science, no one sets out who's doing great science. Well, there are a few, but no one really sets out to say, I want to win awards, right? We're just
right.
all trying to answer big questions. There's a few that want to win awards. Let them
Right.
win all the awards
Then go
they
do
want,
it.
right?
Yeah. Yeah. Yeah.
Just let them do it, right? But you meet these individuals at meetings and you get excited about
Yeah.
questions and you're working together, and then you just gel at a certain level. And not only that, you're in an environment that's just pushing you
Mhm.
to do this, to
Right.
ask generational questions and to work in an uncomfortable environment. A lot of people don't want that. But
You know,
that's a different story.
well, I love that because one of the biggest pieces of advice I give to my students is if something's not making you uncomfortable, then it's not worth doing, right? Yeah.
Absolutely.
Yeah.
Absolutely.
Absolutely.
So I
Absolutely.
wanted to touch, Richard, on
Yeah.
why we went to adenoviral vectors, because
Yes.
it's a very unconventional move at this time, especially because I was working with Jude. So just to give the audience backstory is in the mid '90s, right? Adenovirus was king. Okay.
Mm. Mhm.
And then Ad was this horrible gene therapy trial with the death of Jesse Gelsinger, right? That was led by the trial from the Penn group, led by Jim Wilson. almost decimates the entire field of gene
Sure.
therapy, right?
Right. Right.
And there's
Before it even
books
started.
written
Yep.
on that. But what had happened was at that time point, AD was only leading to transient expression in an
Mhm.
immune competent individual. And not only that, there was a death of a human for an ill-fated trial. So
Yeah.
that research is grinding to a halt. And at that time, Jude was working on this small thing called the parvovirus AAV, that they had this landmark study done here at UNC Chapel Hill that showed that you could put this virus into an immune competent animal. It would last forever, right? As
Hmm.
long as the animal's alive, it kept expressing. And so
Interesting.
the ad starts just declining because the immune problems, right? And all the
Right.
other stuff around it. AAV just is working amazingly. Not understood at that time why, but it worked. So
Mm.
thousands of ships launched into the field of AAV based on these landmark studies by Jude that was done here at UNC Chapel Hill.
Mm.
Now, as everybody knows, right, each viral vector has its strengths
Right.
and it has its weaknesses,
Right.
right? And so the strength of AAV, as is evidenced now by the multiple FDA approved drugs for AAV.
Mhm.
No, I mean, it's amazing, right? It's
Mhm.
transformed the rare disease landscape. That's actually given hope and delivered on the promise of what gene therapy was there
Supposed
for.
to. Yeah.
Okay.
Yeah. Yep.
The one limitation of AAV is this thing called it's called packaging. Okay.
Hmm.
Now, to explain to the audience what packaging is imagine a suitcase and you're going to travel, right?
Mhm.
And you've got to travel for a week, but all you have is a carry-on. Okay. There's no way you can fit all the stuff you need for that trip for a week's trip into a carry-on.
Right.
Now, to put that together is that with the sequencing of the human genome, we know that there's thousands of genes, right, that are extremely large.
Mhm.
And the ability for AAV can only hold about 4.5 kilobases of of foreign DNA. Okay. Now, the calcium channel cDNA, the one that codes the protein, or the Ataxia-Telangiectasia gene that we're interested in that codes the protein, calcium channel is 8 kb just of the protein coding sequence. AT gene is 9.2 kb of the coding sequence, right? It's not going to work with AAV. Not that AAV is not wonderful. It's just it will never work
Right.
um, for certain applications. So what I realized was like, okay, we need something different.
Mhm.
Okay. So there's been a whole industry that's emerged in the field of AAV where they're trying to shrink everything to find optimal things to get it into AAV. And my philosophy in life is like, why play in the sandbox when you've got a beach? Okay.
I
And
love it.
and so there's a lot of people playing in one sandbox, and I'm like, well, I'm gonna go hang out at the beach, right?
Yeah. Yeah.
And there's a lot nature tells you there's a lot of things out there. So it's done millions of years of evolution. So
Right.
could work on that. So
Yeah.
based on this landmark work from others that came before me, specifically Phil Ng, who had developed helper-dependent ad vectors, right?
Mhm.
And
Mhm.
what they've done with helper-dependent ad vectors essentially is they created this what they call a gutted system, took out all the ad genes, converted that into be like AAV, and now you have the packaging capacity of about
Oh, interesting.
36 kilobases of cDNA. Okay.
Wow. Wow.
Now, now you got to remember this ad is developed in the early 2000s. The field for ad vector research is destroyed by
Yeah,
eventually
it's
in the
going,
late
yes, going
90s.
nowhere. Yep.
Ad is put on ice.
Yeah.
Okay.
Yeah, yeah.
And nobody's work. I won't say nobody, but very
Very
few
few.
labs are
Yep.
actively pursuing this as a gene therapy approach.
Sure,
Right.
sure.
So I'm pretty stubborn, right? And I can be contrarian and I could be very iconoclastic, right? But I sat there and I said, well, look, we're very interested in neurological disorders. We've
Mhm.
done a lot of basic research where we've done these landmark studies studying calcium channels because we can do in
Mhm.
vivo work. Well, let's now turn our attention to do gene therapy using helper-dependent nanoviral vectors.
Right.
And so this was probably about, I want to say, when I was at Max Planck, Florida, when we first showed that we could express a calcium channel, I said, well, we're going to go for this.
Okay.
And so I have what I call the Sam Young philosophy, which is the F it philosophy, right?
Yeah.
I don't want to curse on the, but you know what the F
Yeah.
stands for, which
I
is
know what the F. We
sometimes,
all know what it stands for. Yeah.
yeah. So sometimes in life you get to a point and you can talk yourself out of, well, I could do this, I could do that. And you're just like, you just got to do it,
Know it.
right?
Yep.
It's gonna be ugly. You just got to do it, and you're gonna do the work. It's like football practice, or whatever. We got to go down. We got to
Mhm.
get these things done. You just line up in the dirt, and you just keep pushing forward, right? And so I decided at that time point we were going to commit to helper-dependent ad vectors, right?
Yeah.
And so this was working well. And what really spurred me on to really commit was my former football coach at Princeton, Steve DiGregorio. I'd known him a very long time, and I'd known his wife, Nadia DiGregorio, who was a javelin. She's my high school track coach, and she was a javelin thrower here at UNC
Nice.
Chapel Hill.
Awesome.
And unfortunately, their son suffers from ataxia-telangiectasia.
Mm.
Steve unfortunately passed away a number of years ago from pancreatic cancer.
Mm.
But about 5 or 6 years ago, he called me up, and Steve and I are very close. We had chatted, and he's like, Sam, when the hell are you going to get off your ass and do this? And I'm like,
You're like, I'm in, coach. I'm in.
that's it. And I just was like, that's it. I'm in. I hung up the phone and I'm like, that's it. We're going down there and we're committing full on to doing these things. So
Wow.
I immediately started moving my research towards that gene therapy. So
Mm.
to set it up for the audience so they understand what's happening is that
Yeah, please.
the brain is composed of thousands of different cell types. Okay.
Mhm.
Each cell type does different things in the brain, and it's important for different functions. Okay. However, each cell type has what they is called a tropism, or
Mhm.
the ability for a virus to get into that specific cell, right? And so you can think of a lock and key, right? So you've got your key card for your hotel room. All the doors look the same, but your key card only works on one door. Okay. So viruses will go into certain different cell types or they won't. And we now know a lot of this has to do with what they call a receptor that determines the ability for the virus to get in. Okay,
Yep.
great. So a lot of these neurological disorders we were interested in Ataxia-Telangiectasia or CACNA1A disorders,
Mm.
they have a massive component of cerebellar neurodegeneration.
Mm.
Okay, so your cerebellum does a lot of different things, but what happens is there's a specific cell type called Purkinje cells that degenerate and die. You develop ataxia, and
Mhm.
eventually the whole cerebellum degenerates, and you have shortened life, and
Yeah,
which is terrible, and all these different things. So
sure.
so one of the things was I never, I if I'm going to do it, I'm going to do it, right?
Right, right.
And so for 30 years, adenoviral vectors can't transduce Purkinje cells.
Mm.
Okay. So
Interesting.
now we've got this whole thing of like,
You got a new challenge.
that is dead for neurological research, even though Bill and his groups have shown the efficacy of this, that it works really well in preclinical animal models. But now the cell type that I'm interested in can't get into the viral vector I need, can't get into there.
Right.
So when I was at Iowa, they had this program, and I really want to thank Iowa for doing this. And Kevin Campbell at that time point was really instrumental in establishing it. They had this Iowa Distinguished Scholar Award,
Mhm.
and so you had to apply for it. And I had this, like anything, got to have crazy ideas, and I applied for it, and I won it. Right, so you got
Nice.
$200K a year for 3 years for unrestricted cash. Okay.
Wow.
And so what I decided to do was I was going to take all that cash and burn it and develop whole new adenoviral vectors to transduce Purkinje cells, right?
Mhm.
So it was completely crazy, it's completely risky, but as I feel about it, in this sense is like I kind of talk about like something called doing chimp science, where you're just a chimp ruling over the jungle and you just got to go out and push every day in the jungle, right? And so I decided we were going to go full chimp, right?
Yep.
And then basically go forward. And I just said, we're going to solve this problem now.
Sure. Sure.
And so together with my postdoc, Emra Cool, and my graduate student, Uchechi Okorafor, we went after this, right?
Hmm.
So we had taken, there was a trick, was that Mike Oldstone, this is why, as Arnie was right, if you're a virologist, you can do
You
anything,
know everything. Yep.
right?
Yep. Yep. Yep.
So Mike Oldstone, and this is why you've got to be able to move through fields, is that Mike Oldstone in the late 90s was trying to develop a mouse model that would
Hmm.
be susceptible to measles.
Hmm.
Okay. Why is that important? The measles virus only infects humans, right? And some certain classes of New World monkeys, right? And so, but they can carry so there's the CD46 receptor is specific. So measles interacts with the human receptor, not the other murine or these different ones. Well,
Okay.
Mike had this wonderful idea and developed this where he made the human CD46. He took that receptor, put it into a mouse, and then showed these mice were now susceptible to
Mhm.
measles.
Hmm.
So, I'm extensively reading the literature, and, people say, oh, you get lucky a lot. And there's that the old thing about law school, right? Not that I've gone to law, but someone says, yeah, I get lucky a lot at 4 a.m. in the library,
Right.
right? So massively reading, I have this idea. I'm like, wow, Mike Oldstone has made this animal model. We can take
Sure.
this animal model and screen our viral vectors in there. Okay.
Hmm.
Now, why is that important? Right. So I'm just walking your audience through this.
Yeah.
It's important because you want to be able to have a viral vector that you will have high confidence that it works in humans. Okay. There have been countless viral vectors that transduce everything in a mouse, transduce everything in a dog, and then it goes on to a human and does nothing.
That'll work.
Okay.
Yep.
And we'll get to this later, but that's a crux of that's a big challenge in the field at this time point. So
Mm.
I did not want to, as I tell people, I'm inherently lazy. I want to do the least amount of work
I don't think you're lazy.
to get the biggest output, right?
Yeah.
So we make a bet. And I said, I'm going to bet if we can get this human CD46 mouse, we're going to take has natural tropism. There's a class of vectors that use this receptor, and then we'll see if it'll work in these neurons. Okay.
Okay.
Okay. So big project now, because
Yeah.
now what we have to do is we have to create chimeric viruses that have the domain that interacts with this receptor across ad. Okay.
Okay.
So we took this trick again. There's no geniuses in the world, right? It's no geniuses, right? It's a lot of
Right.
smart people working on problems, right? So there's a lot of smart people who have been trying to develop oncotherapies
Hmm.
using ad vectors, right? And what it turned out is that the common ad vector that had been used, right, ad type 5, they would not get into these cancer cells because they no longer express that receptor. Okay. So they had developed a bunch of technology to say, hey, we can swap this fiber domain, which interacts with this receptor, to get that into these cells. Okay.
Hmm.
And it kind of worked. So I said, well, look, on the shoulders of giants, it's that
Giants, here we
I
stand.
see. So let me take these other smart people's work, modify it to what I need to do. And so we modified it. We took these group B vectors, and then I said, okay, I've been challenged by Steve to solve this problem,
Right.
right? And I wanted to work on calcium channel disorders, but I'm not going to go out there to any foundation yet until I can tell them I can transduce these cell types, right? So we're building. Ember's working his butt off. Uchechi, we're just going after this. A lot of stress, get the animals. And then on the Sunday, I'm in the lab, just because you got to catch up on stuff. You're trying to balance family life and everything else. And you're like, okay,
Sure.
I'm in Sunday to catch up. I run into Emra, who's, because we've got a time point to check. I'm like, hey, Emra, what's going on? He's like, I got the news. I'm like, what's going on? Right. He's like, I don't want to tell you because I've only seen it once. I'm like, expletive, excellent. Tell me
Yeah.
now.
Tell me
Right.
now.
and it worked. It
Wow.
went into the Purkinje cells. So we did this whole massive
Amazing.
study, right? That we've got a provisional patent on this now.
Hmm.
We published this. So we've developed a whole class of viral vectors in a humanized animal model that will go into the cell types we need. Okay. So now we have this, right? I'm like, okay, now let's reach out to CACNA1A Foundation and
Sure.
AT Foundation, and I can tell Steve at this time point that we've got this. And like sometimes serendipity happens. Like a week later, I get an email from the CACNA1A Foundation, dear Dr. Young, and I'm like, first of all, no one calls me Dr. Young,
Who's this?
right? Just call me Sam. And so um, would you be interested? We know you work on calcium channels. Would you be interested in working on this therapy, to develop therapies? And I write back, absolutely. Actually, I was just emailing you. So now
Crazy.
what we've done is develop this platform technology that allows us to go after big genes. Okay.
Hmm.
And for all of those out there that say, well, we know there's this immunology issue, right? The central nervous system is immune privileged. And we know that you can go in with ad vectors. Pedro Lowenstein, Maria Castro have already shown with helper-dependent adenovectors, you get long-term stable transduction. And they've actually got a phase 1 clinical trial for glioblastoma that the ad vectors are working well. Okay.
Wow.
So now we've got this ability now to do this. And now the next question is, why is this important, right?
Hmm.
So why are having this extra capacity important? Okay. Well, genes, what is it emerged is with AAV, right? You've got this small packaging capacity. So they were trying to build transgene cassettes just to get expression. Okay. Now, what happens is you're going to go into a human being, and the goal is, the premise of gene therapy has always been single shot lifetime correction. Okay. Now, your proteins are being expressed at different levels throughout the days, throughout, response to stress or not. And they have these other things with the sequencing of the human genome, right? What they found out, again, this another huge thing done in the 90s and early 2000s, funded by the NIH, right? That's why NIH funding is so
So important.
important, right? Is that they figured out and they discovered that there are all these regulatory elements that didn't make protein, but they controlled gene expression.
Okay.
So you want to have those regulatory elements in there to make sure your gene is somewhat being mimicked properly for expression, because you don't want to make too much protein because that could be bad, right? And that could
Hmm.
lead to effects, right? And so now what we're doing is we have that ability to take those proteins, put the right regulatory elements on there, and
Hmm.
now go back in to treat these diseases. So that's where we're at now. And so now we're basically pushing forward heavily on ataxia-telangiectasia and pushing heavily forward on CACNA1A disorders. And we want to go into the next level for all other big disease genes, such as Huntington's,
Or
that can't be treated by AAV vectors at this time point. Now, of course, there's lentiviral vectors, right? I don't want to, just for the audience out there, there's other vectors. Each virus will have its niche for doing excellent things. Just so the audience knows, CAR T therapy, right? It's gene therapy where they use, lentiviral vectors or retroviral vectors to transduce stem cells to cure your cancers at this time point.
Sam, there's so much that you've done here, just like from a grit and a sweat and a pushing
Yeah.
forward perspective. How do we scale this? I mean, how do your research efforts get scaled? I mean, beyond the obvious, beyond the funding, but there's tremendous potential in what you're doing. You just mentioned Huntington's disease. How do we scale this or accelerate it and keep it accurate?
Yeah, yeah. Richards, this is, the billion-dollar question
Right.
on how do you do this. So this is what really attracted me to move into this and to come to UNC Chapel Hill.
Mhm.
Okay, Dr. Stephanie Davis, right? She's the chair of pediatrics. She runs the the children's hospital, right? And
Yeah.
they're building a new children's hospital down here, and
Oh,
it's going up in about 7 years. So
Wow.
Why am I mentioning Stephanie, right?
Mm.
She's an amazing colleague, right? But what you need is this bridge between the clinical side
Mhm.
and the basic side.
Mhm.
Okay. And you need that infrastructure. Okay. Because what you need is you need clinicians who see the patients to tell you what needs to be done, and you need to have marker studies, right? Okay, how many patients, what's the age of treatment? I mean, that's a whole other area of things, to be able to do.
Yeah.
Then what I'm setting up here is to develop GMP facilities, right? Essentially to produce these vectors, right? So you have to have biomanufacturing, right? And this has
Right.
been something that's been established here at UNC. They have the Advanced Cellular Therapeutics facility where they're doing a lot of CAR T, and now we're going to build out a whole AAV component over there.
Oh, wow.
So you have to have manufacturing, okay?
Right.
Then you have to have basic research, and then you have to have an understanding of the disease, right? And so what you need is teams and
Mhm.
groups of people in one location that communicate with one another, right? So we could develop, everything we want in the lab. Great. All right. Wonderful. Does it work in a human? We don't know. Okay,
All right.
how are we going to be able to do that? So what UNC also set up is this clinical regulatory, the CRA, clinical regulatory group, right? And they help basic researchers start to prepare to get things to be brought forward for clinical trials, right? So how are you going to move is massive commitments of infrastructure to do these things, because yeah, I have a viral vector now. I can show that it corrects function in a preclinical model.
Right.
Wonderful, right? This is what any VC is going to ask. Okay, so you can show an animal model. What's your next step? Okay, then we got to get the preclinical. Okay, how do we get from preclinical? How do we do a phase one?
Yep.
That is not something I know. I'm not trained to do that.
Right.
So you got
You
to
need
work
someone
with
who can. Yep.
and working with the clinicians, right? I mean, so having this they're the ones on the front line seeing the patients, and then they know what's important, because one of the other things that needs to be established is that what we don't know is what are the time points of intervention,
Yeah.
any cells do we need to transduce, right? And it's just not known, right? I mean, they kind of, you see patients when they present in the clinic, but if we have these animal models, we need natural case histories of animal models. But it's a push and go, and one of the things was you need clinicians to tell you, because you're developing a therapy of like, hey, this is going to work, that route of delivery is not going to work. Oh, actually, if you could cure this, that would I wouldn't have to see my patient, 20 times a year, would go down to 2. And you're like, really? Well, we could do that. And I think that's really important. And I think,
Mm.
at UNC, you saw this here with their development of hemophilia, right? So
Right.
Paul Monahan with Jude Samolsky developed these hemophilia, the technology for curing hemophilia B. This Paul's gone on, but this resulted in CHL Behring's hemogenics. But this
Right.
was essential because there was a whole blood resource center here, a
Mhm.
disease group here with dog models, and you had that integration. So you really need to have integration across things. It's big, and that's what's really going to be to do it, because the classic way I would think about is if people have seen the movie Oppenheimer,
Mhm.
or if you've read the book, the Roderick Rhodes books, The Making of the Atomic Bomb, right? What you see is you've got a group of great scientists together, world class, right? And then what you needed was Oppenheimer to run this thing, but then you needed full force of the government. There were so many other things that made that
So many
happen.
integration points.
This idea of some lone genius, and then it's being presented in society now. It is no lone genius. You
There's no
need
such thing. Yeah.
exactly. You need integration, and I think that's what was really exciting, and that's what we're pushing forward here at UNC.
I really, I worked on cardiac pacing and electrophysiology in the late '90s, early 2000s. I think you and I talked about that, and we were struggling at that time to integrate bench science, basic science, clinical clinicians, and I think of how much that has advanced. And to your point, without that integration, you can't get it done, right? You need that. You need that integration for sure. So speaking of exciting things, Sam, like what's next on the immediate horizon for you? What are you kind of most excited about and wanting to focus on before we let you go here?
Yeah, so I can give you 2 levels. At the lab level, I'll give you the lab level, at the center level, okay?
Sure.
So at the lab level, what we're super excited about now is that we've developed technology now to be able to transduce almost the entire cerebellum in a mouse model,
Wow.
okay? For all these Purkinje cells. That's another crazy thing, right? So we've been working on that because we need to say how many cells do we need to transduce. So we've developed that. We've got animal models now that we can knock genes out for Ataxia-Telangiectasia. We can do it for CACNA1A. And
Right.
now we're at the point now is we can do the real experiments of let's replace this and then put that gene back in. So super excited about that. But we're also moving into, so we can show it. There's another problem, and this is what made AAV so accessible was production.
Yeah.
AAV can be produced just by about anybody now, right? So that
Mhm.
production technology is developed here in Jude's lab. The issue with making helper-dependent ad vectors is it's kind of still a little bit, and not messy. It's just it's difficult, right?
Okay.
And it's not amenable to scaling if you're going to try to make a lot of vector for, doing thousands and thousands of individuals. So
Gotcha.
we're gonna move back into trying to solve production issues. We're excited about our disease models, right? That allow us to go in and then basically again take technology. shRNA is approved; it's FDA approved, right? And I think, combining shRNA to knock out disease alleles, then put back wild type, I think is there because for at least for a lot of diseases where you need chronic expression of a protein, this idea of CRISPR editing or CRISPR-I or CRISPR-A,
Right.
that's not feasible at this time point because you have to have a chronically express these proteins. CRISPRs, they're never been seen by the body. You're going to get an immune response. So we're trying to slowly build. Not to say that CRISPR technology for
Oh,
brain
sure.
disorders is not going to work. I just don't know in the next 10 to 20 years if you're going to chronically express CRISPR because if you think about this in a way, you are going into someone's child, you know, at age 3, maybe 4,
Yeah.
maybe 5.
Pretty frightening.
And so you're going to say, okay, now I'm going to express this for the next 20, 30 years for the lifetime. And so do you want to farm? We don't know what would happen with a foreign protein being
Right.
expressed.
Right.
Now at the center level, what we're really exciting is we're massively building.
That's
Okay.
cool.
So the center is going to be focusing on generational questions, right? It's not a 5-year question. We got to focus on generational
Yeah.
questions
Yeah.
because,
Yeah. I gotcha.
at the end of the day, is I abide by this one philosophy, right? We do not accept the world for the way it is. We are moving towards creating the world the way it should be,
Should be. Yeah. Nice.
right?
Yep. Yep.
And that's a lot of commitment to do that, right?
Right.
So this is not about making companies, making money. It's not about winning awards. It's about solving these problems because at
Hard
the end of the
problems.
day, the rare disease community, I would say, is the last unfortunately, legally community that's discriminated against,
Yeah.
right? At
Hmm.
many levels, right?
Yep.
Insurance doesn't want to cover them.
Yep.
Pharma doesn't want to do research into it because it doesn't make enough
Doesn't make
money.
money. Yep.
It's not that pharma's evil, right?
Yep.
I mean, it's so the question is, it's up to academia for us to carry that mantle forward to advocate for the rare disease community and develop these therapies. So, what are the key things we need to solve, right?
Yes.
Okay. Key things are we need to have multiple different delivery systems to go
Hmm.
in. So you want to say, hey, you've got this disease. Hey, we'll go with AAV. That one will go with a helper dependent ad. That one, for stem cells, we'll go with the lenti for, for amplification for bloodborne disorders. Or there's next level technology. We'll do lipid nanoparticle delivery and all these
Right.
different things, right? So you have delivery. The other issue, and this is a generational question, is repeat administration. So the field of gene therapy has remained unchanged. The number one problem in gene therapy has been delivery. The number
Mhm.
two problem has been delivery. And the number three problem has been delivery. Okay. So once you solve one, two, and three, the next question is repeat administration. Okay.
Yeah. Yep.
What do I mean by repeat administration? Okay. You have this wonderful thing called an immune system that keeps you alive. Okay.
It's pretty good.
And so when you have a vaccine and you're given a vaccine, right, you have an immune response that prevents you from ever getting that virus again. Okay. And that's great. Now, what's happening is when you do the gene therapy, you're giving individuals all the viral vectors to get in. And so the question is, you're counting on that level of expression to maintain. Okay.
Mhm.
So one of the issues, to put it in perspective, is that for DMD, they've done phase one clinical trials. There's the Kern family that they were down here, for Jude's Festschrift as for his Festschrift retirement
Sure.
party. But they treated their son and then worked beautifully. But now, as the child is growing, they're losing expression.
Interesting. Huh.
Okay. So now what becomes is repeat administration becomes very important, right?
Yeah.
But
Yeah.
the issue is you have an immune response against that viral vector.
Right.
So what you want to be able to do is to say, hey, this is coming down 5, 6 years later because you've grown or you've lost cells or whatever.
What
We
have you?
want to be
Yeah.
able to go back in, but not having a massive immune response that kills you.
I get it. Yep.
Okay.
Yep.
So we're looking to hire, to get people that work on the immunology front, right?
Mhm.
And essentially to say, okay, we need to do immunology. We need to understand how the immune system works so that we can manage that, so we can do repeat administration, so that if we treat you at year one, 6 years later, 7 years later, you're like, okay, we need to put the gene therapy vector back in. That's a huge question. I think the other thing from a bioengineering standpoint is manufacturing, right?
Yep.
Is how do you create enough vector at mass scale?
Sure. Yep.
Okay. And that's not an easy issue. And why is that important? Because you're making a million billion, you need a million billion particles to get into a human if you're treating systemic delivery. Maybe you need 1,000 billion to do a brain disorder, but you need to be able to produce this and it's got
A
to be
lot.
reproducible. So you want to have ways that you can do effective manufacturing so that it works very well.
Yeah.
The other generational question is that we're attacking is it's a very simple one. Why do we need so much viral vector to be able to transduce and deliver these genes to the cell? So to put it in perspective, you're giving an individual a million billion particles, right?
Mhm.
You never see that amount of virus in anything, right?
Right.
So what's happening is that we don't understand why you need that amount of virus to be able to do that. So there's got to be going back. It's the old Max Planck principle, which is
Yep.
insight must precede application. Okay.
Mhm.
And so that we've got to understand what are the rate limiting steps that are controlling gene expression from a viral vector. So
Mhm.
if you can do this fundamental science, lower the amount of viral vector needed to transduce, let's say by 2 logs, right? You've lowered the risk of an immune response or bad things happening. And not
Right.
only that, you've now lowered the amount of manufacturing you need to do.
Need to do it. Yep.
Right. So these things go hand in hand. And then I would say from probably the next thing is to develop different genetic animal models.
Mhm.
Obviously you want to be able to go into certain rodent models, but rodents aren't humans. And then, you'd like to be able to do different things into larger animal models that more reproduce the human condition. And I say this because cancer's been cured, thousands of times over in mouse models,
Right. But not human. Yep. Yep.
but not in human. And it's
Mhm.
not that, and we all know this, so we want to try to work to get better systems. So I think those are the critical issues, right? And the other thing, I think what needs to be done and promoted in this case is continued advocacy,
Mhm.
why this is important, right?
Yep.
And then also to build continue to build public-private partnerships because while academia can do certain things very well, it does other things very bad, right?
Right.
So
So you need the
academia
private.
is excellent for early stage investigations, right? And then essentially private is absolutely excellent for late stage development. And so
Right.
from that standpoint, we need to work hand in hand with those two things. But all those things are here at UNC Chapel Hill,
Yep.
right? And I think that's where we're moving towards.
Just more evidence of that, we need to be integrated in everything that we're doing, whether it's the research, whether it's the advocacy, whether it's the public-private partnerships. The integration is so important. So thank you, Sam. We have been speaking with Sam Young. I'm not going to call you Dr. Sam Young. I'm just going
Don't
to
call
call
me
you
Dr.
Sam.
Simeon,
Sam
right? My
Young.
buddies, I would say this, my buddies in college, they'll know my nickname in college was Stump, right? So at that time, I was 5'10", 265. And
I
so,
love it. I love it.
right. So
I
at
love it.
that time point, you call me
No,
Sam, my friends call me Stump, right? But at the end of the day, Richard, I really want to thank you and your
yeah,
audience for the opportunity to speak. I think this is really important.
you're welcome.
It really takes a team, like individuals,
Yep.
all of us to put this together because that's how these things are going to be solved. The only heroes in this, all right, are the patients and the patients' families, right?
Right.
And I think
Right.
that's what has to be
That's why we're here.
absolutely, that's what we're here for. And, we're public servants here to serve the community.
Yep.
And we thank, the rare disease community, and we thank, the American taxpayer for allowing us to develop
Do
these
this work.
cures,
Yep.
right? Disease strikes everybody, right?
Absolutely. No
And we want to
discrimination.
be able,
Yep.
we want to still be there and provide hope for everyone.
Right. Well, thank you, Sam, for doing that. Thank you for doing the hard work to provide us with hope. And we'll keep in touch and continue to watch what you're doing. Thank you again, Sam.
Thanks so much, Richard.